Hello, this is a continuation of a tutorial on how to use Advanced Peripheral Bus to interface to your control status registers. In the first part of the tutorial, I showed how to instantiate the AXI APB bridge in Vivado block design, how to export an APB port from that bridge, what that port looks like at the ports to the wrapper around the block design, and what the logic that interfaces to APB would look like. The logic that uh, implements the read access and the write access. At the end of that tutorial, I compiled the design into a bit file and then exported the XSA, which I dropped into a folder named Vitis. Vitis is a folder I create that resides underneath the project folder I use. The project folder contains the Vivado GUI folder, which has the Vivado project, the Vitis folder containing the Vitis project, an RTL folder containing all the Verilog, VHDL, as well as the Vivado generated IP, including the block design constraint folder containing the XDC and SDC files. I guess in this case only XDC, the physical and timing constraints used by Vivado. I also have a C source folder with all the C source files that would be used by the Vitis project. I like to keep the source files outside of the Vivado and Vitis project files because I like to be able to go in and delete everything uh, in that folder to start fresh. And that's what we are going to do today with the XSA. We're going to go ahead and open up Vitis. We're going to import the XSA and build an application from the C code up there in the C source folder. So let's start. Now, I went ahead and I downloaded Vitis 2024.1, which includes Vivado and so forth. And I tried to run the new version of Vitis and I failed. So I had to go back. Fortunately, there's still a Vitis Classic 2024, which works just like the previous versions, the 2023, 2022, and so forth versions of Vitis. So I'm going to go ahead and open that up. And there we go. I'm going to browse to the project folder, and I'm already pointing to it. I'll launch Vitis. I will go ahead and create an application project. I'll create it from the XSA file. I'm going to give it a name of, first I'm going to browse and find my XSA. There it is in my Vitis folder. I'm going to give this a name of default name underscore platform. Let's see if we can spell that correctly. I'm going to copy that to make life simple in the next few pages. I'll name my app default name underscore app, and I'm going to name the system default name underscore system. Took too much. Create new. This is just going to be standalone bare metal MicroBlaze and hello world. So we'll start with hello world because that gives us the infrastructure we need created the Hello World app, and I might even go quickly test it. I'll go ahead and do a build. Let me open up Terratorm while that's happening. Set up the baud rate that I configured the AXI UART to. 11, 15, there we go. And I'll go ahead and run this. Let's see what happens. It'll download the bit file, and it should start executing the Hello World application, which resides in local RAM here on my little Digilent Arty S7-25 board. So there we go. All right. So what's next? We've run Hello World. Now we have to write some code that talks to our advanced peripheral bus slave that we've put into our Vivado or into our hardware. So how do we find the APB? It has a base address somewhere. And the way we find that base address, if we haven't memorized it from the Vivado project, we're going to go ahead into the platform and find the board support package that's been generated from the XSA. Open up the host CPU include folder, and I'm going to scroll down and locate a file named xparameters.h and open that up. I'll go ahead and maximize this window. xparameters.h defines for all the hardware base addresses as seen by the block design in Vivado. And just for fun, there's a lot of them, particularly associated with that MicroBlaze, but I'll do a search for APB_M because that's the instance name given to the advanced peripheral bus master interface. And there I have a define that sets the base address to this value. It's much more convenient to use that define than to try to remember that address. So now that I know that, I make sure that I use that base address in my C code to communicate with my advanced peripheral bus slave, because that address could change, particularly in the case where I add another slave interface. So I've got M1 and M2 and so forth. By using the defines, it doesn't matter where Vivado ends up mapping the base address of the various advanced peripheral bus master ports on the block design. All right. So that said, I'm going to show you a little trick. I started with the Hello World application because that gives us a bit of a head start in terms of getting an application up and running quickly. But now I want to run my code. I've got a ready-made application that implements a command line interface, something that I cobbled together from a Xilinx example design years ago. Right, so now, how do I transition from that Hello World example to my code? And here's the quick and easy way I choose to do it. Here's Hello World with all its linker script, the hello world.c application, printing out hello world text. What I'm going to do is right mouse click on source. I'm going to import sources from my C source directory. I'm going to select the C source folder. Go ahead and click on that, which will select all the source files in that folder. And here's a little trick. I don't like when Vitis takes control of everything. I want those source files to stay exactly where they are and not get sucked into the Vitis project folder. So I'm going to click on Advanced, and I'm going to click on Create Links in Workspace. And that will allow the files to continue to reside exactly where I put them, exactly where I'll go look for them and edit them later, rather than having Vitis suck them into the source folder underneath the Vitis project folder. So here I go, finish, and yes. All right, so now in the C source folder here, which is just a link, not actually residing underneath the source folder, I have my source code. One of those pieces of code is main.c, which is a drop-in replacement for hello world.c. All right, hello world.c has its main, init platform, cleanup platform, and a few prints. My main.c, I've replaced those prints with xylprintfs, which is a low overhead version of printf. Keeps things small because we're running out of internal RAM. And I'm within this file, I'm going to print out a little introduction, and I'm going to jump to my command line interface test. We'll walk through that later. But first, let's do this. Since I already have a main, I'm going to go get rid of hello world. I'm just going to delete it. Okay. Let's go ahead and rebuild with what we have. And let's go ahead and run it just for fun. And there it is. There's my command line interface. It puts up a very simple menu, just single characters. If I want to run function 0, I press 0. Function 1, I press 1, and so forth. Let's do a very simple one. I'm going to press 2, and it's going to read that user data, that 32-bit word that's embedded into the bit file during the Vivado build. I'm going to decode that. That puts a timestamp in there. And I can see that that was built 2 days ago at 4:48 p.m. So that's the last build I did when I was doing the Vivado part of this demo a few days ago. So let's go ahead and look at that command line interface file. Here it is, CLI test. And what am I doing here? I have looks like I haven't deleted the residual here, but let's simplify that. I have defines for those 4 status registers and those 4 control registers, the base addresses. And how am I deriving that? I'm using the this value dug out of xparameters.h that defines the base address of my advanced peripheral bus master port. And I'm adding to that an offset for the status registers and for the control registers. Now, since my registers are long word, 32 bits wide, the byte offset is 4 for each location in the address map. So my base address contains, if we go back to the Vivado project, my base address is my version, and then the next address up is status register 0. After that, 1, 2, and 3. And then at midway through my map, I start with my control registers 0, 1, 2, and 3. So I've set up base addresses just to keep the code more compact. And now I'll quickly show you how the that user access word is decoded. This is all out of one of the many Vivado user guides. I can't remember exactly which one. I should have documented it here. But we have the year, month, and days, and we have the hours, minutes, seconds from that 32-bit word. It's embedded in the bit stream. And here's how it's decoded. And here's the printf that we see when I press 2 to run this function 2, so forth. We'll jump, this has nothing to do with APB at this point, but let me just jump down to this very simple command line interface that I acquired from an example design. It starts with my command line interface test function, which prints out a simple introduction and then enters an infinite loop where it calls a function called display menu, and then calls a function called parse main menu. So display main menu displays a simple menu, just a bunch of Xyle printfs telling me, okay, if I press 0, I'm going to call function 0, and so forth. And then the next thing is parse menu, or parse main menu. Parse main menu calls a function named inbyte, which is a Xilinx function, part of the UART interface. So it'll wait forever for a character to be pressed. The 8-bit character value goes into the variable input, and then I have a little switch case statement here where I look for the 0, 1, 2, the single character code, and then I invoke the function associated with it. Very simple, really easy to reconfigure for any application. I use it a lot to test hardware before I throw the hardware over the wall to the software team. All right. So let me just do a quick demo of the interface to the LED blink function and the interface to the pulse width modulation function. These are 2 bits of hardware that I interface to through my advanced peripheral bus control status registers. And I'm trying to recall, here we go, our blink frequency test. We had an 8-bit value that we put into control register 3. So I set up a variable named address. I'm pointing to control register 3. I initialize blink frequency to 1, which is 1 hertz. And then I do a little poke. Now, PL poke is just a simple wrapper on top of some low-level Xilinx interface routines. I'll just quickly show you what that looks like. PL poke just calls Xyle out 32. I've got PL peak, which just calls Xyle in 32. They're just simple wrappers. This was created at a time where we were doing both bare metal and Linux. And so we just had a set of functions that would allow us to peek and poke through bare metal, and then we had another set of functions that did the same thing from the Linux environment. All right, so PL poke is just writing the value blink frequency to this address, and then I go into an infinite loop here where I wait for a character to be printed. That character could be either U to increment the blink frequency, D to decrement the blink frequency, or X to exit the loop. So here I am, I'm calling inbyte, and then I check to see if it's a value of X. Sorry, if it's a value of X, I exit the loop. If it's U, I increment up to the maximum value of blink frequency, which is 8 bits. If it's D, I decrement down to the minimum value of blink frequency. Easy test of hardware, right? And then up to duty cycle sweep. This is where I have a function that has an 8-bit input to a pulse width modulation module. And that pulse width modulation module directly drives the green LEDs. So what do I do here? I set up the address once again to control register 3. I initialize the duty cycle to 0. Now, in this sweep, I start with the duty cycle 0. I increment it up to 255, and then I decrement it back down to 0. And I just do that continuously until somebody types X. So let's demonstrate that. I'll go ahead and run this. And there's my little Arty board, which we know and love. And here's my duty cycle sweep. I'm going to hit 4. And those green LEDs are going to get gradually brighter and dimmer. Brighter and dimmer until I hit X. So there I am interacting with the hardware. Blink rate test. That's a 5. There we go. Blinking at 1 hertz. I'm hitting U. Incrementing the blink rate. Hitting D. Decrementing that blink rate back down to 1 hertz. Hitting X. I'm out. All right. I hope you enjoyed this demo. And good luck on implementing your next set of control status registers using the Advanced Peripheral Bus APB AXI bridge. Take care.